Welcome to today's seminar. Thanks very much for joining us. We just one quick order of business. Please just remember to stay on mute unless you have a question, in which case you can either unmute yourself and ask during the talk or after the talk. You can also type your question into the chat if you want, and I'll ask it on your behalf at a convenient time. So with that, we're delighted to welcome Dr. Charles Rahal, an associate professor in data science and informatics at the University of Oxford and a former British Academy postdoctoral fellow. His work focuses on the open science movement and includes maintaining interactive projects like the GWAS Diversity Monitor and Robustify. In addition to holding positions as a co-investigator and principal investigator on various research projects, he's an associate editor-in-chief for the Journal of Social Computing, consults for the Banco de la República, and holds an honorary visiting professorship at Peking University. He also leads the Metrics and Models Lab and recently co-founded a data science consultancy company, Patterns and Proofs. So we're so happy you could join us today. Charles, take it away.
Thank you, Ravi, and thank you, Clint. It's a real honor to be able to give this talk. As I was saying before some of the participants joined, this is a project I've been working on for 6 years, and I'm going to have one slide which kind of tells the origination of this project as we go through. It's been quite a journey, and so I'm really keen further to be some discussion. I'm very happy to take comments or questions throughout the hour or so that we do, the 45, 50 minutes that we do, or at the end, I can finish a bit earlier, but really keen for some feedback, constructive or destructive, because this is probably the last time that I present this before we submit it to a journal for hopefully editorial and peer review consideration. So the theme of the talk is on the responsible use of random number generators. I'm guessing that you all have differential experiences and ideas of what I mean when I say pseudo-random number generators, but let's start with some more definitional aspects. So we asked everyone's favorite probabilistic machine at the minute, probably GPT-5 Mini, on exactly what a pseudo-random number generator is, and it returns with that which is on the slide. A pseudo-random number generator is a pseudo-random number is a value produced by a deterministic algorithm, a pseudo-random number generator, a PRNG, that's intended to mimic the statistical properties of true randomness. The important thing here is that we're talking about pseudo-random because this stream of almost random numbers can be reproduced. These things, as we're going to argue, very much form the cornerstone of academic inquiry. Even GPT recognizes that a PRNG is really important for applications to be reproducible. We can reproduce these states if we know something called a seed, and if we know the type of algorithm that we use. We're quite lucky in academia that academic kind of consensus has more or less settled around using one type of pseudo-random number generator, the Mercian-Twister 64-bit variation. This is really important, and we're going to talk about one example when we use a lower bit rate than 64 bits and how that has issues for pseudo-random number generators with regards to collisions. So we're talking about ways to generate streams of random numbers in a way that is in principle reproducible. If we wanted to, we could get the same stream of random numbers twice, and this is a really important idea for reproducibility and integrity within the scientific record. And that's more or less viewed as best practice at the minute. And we'll talk more about what best practice is exactly as we go through the slides. I'm going to argue that this is actually incredibly dangerous. However, pseudo-random numbers are just one type of random numbers. If we query the wonderful OpenAlex resource, some people in the room might be aware of OpenAlex. OpenAlex is a large-scale bibliometric database that tries to index the entirety of the scientific record throughout history. It's currently got about 250 million rows of bibliometric metadata within it, and we wanted to see how often academics are talking about, mentioning random numbers. We actually think it's somewhere about 3% of all papers in their abstracts mention some form of random numbers, pretty big. However, when we then combine this search term with something like a hardware and random number, a quantum and a random number, a pseudo-random number, or a quasi-random number, these things then become a bit less prevalent. Random numbers of certain specific types are discussed much more infrequently. There are many more papers published in computer science to do with pseudo-random numbers than there are in other academic disciplines. If we look at something like the ANZARC fields of research, the FORs, computer science is the most actively represented in terms of people who are actually thinking about, caring about, writing about pseudo numbers. However, interest in pseudo-random numbers has increased fivefold or just over fivefold, I guess. However, still extraordinarily sparse. There's only 0.0048% of papers that talk about pseudo-random numbers. And I'm going to try and persuade you and convince you that pseudo-random numbers are one of the most, if not the most, underappreciated phenomenon within all of academic research today. I think that this is a bold claim, but hopefully by the end of the talk, I'll have been able to win you over. Let me try and do just that. If we're Python users, if we're R users, you're going to be familiar with something like the random module. We can generate a list of floats in this range of _ to 5. We're going to print out that list, and it's going to give us 5 random floating point numbers uniformly distributed between 0 and 1. Hopefully, this concept is relatively familiar to some of you. If we want to generate some random numbers for any purpose, whether we want to simulate flipping a coin or do something more academic, maybe, we can very easily do this with 3 lines of Python. We could have done this in 2 lines of Python if we'd have really wanted, or 1 line if we'd have stacked the import and the print statements together, just like we could do this in R in a similarly small amount of code. The problem, however, is if we run this code twice, we get 2 different sets of random numbers. This is really important because pseudo-random numbers, although they're not discussed in the titles or abstracts of more than 0.00048%, they actually occur everywhere. So in the computational sciences, they occur in numerical integration, cryptography, genetic algorithms, signal processing, deep learning, weather forecasting, procedurally generated content, and many more other academic fields within the computational sciences. And within the applied health or social sciences, not least the social data sciences or computational social sciences, this occurs in times when we might be splitting our surveys for treatment, allocating treatments and controls. It might occur in bootstrapping. It might occur in some kinds of epidemiological modeling when we're doing simulations. It occurs in econometrics. It occurs in when we're imputing data. It occurs when we're topic modeling, when we're building our agent-based models, and many other types of research design. PRNGs form the cornerstone of most modern computational methods. They're not essential if we're thinking about deterministic algorithms like linear regression, when we're simply deterministically calculating the product of some matrices and vectors. But if we think about any other type of gradient descent, any other type of maximum likelihood with some caveats, any other type of research design which involves some kind of a random draw, hidden or explicit, this occurs everywhere. There are many times when we're learning our econometrics or our statistics modules at undergraduate degrees, and we're using some packages or libraries, they will, under the hood, use random number generators without us having to explicitly see it or be aware of it. And I would argue that because of the way that random number generators are hidden within statistical packages, we as a scientific community have maybe become a little bit blindsided to just how common and important random number generators are within the academic process. As I mentioned at the start of the talk, we're using the Mercian Twister 64. This is ubiquitous. This is a very commonly accepted type of pseudo-random number generator that is the main modern implementation in R, Stata, Python, Excel even. This has come to be known as the main way of producing these reproducible streams of random numbers. There is a movement to say that it's about time to get rid of the Mercian Twister. I don't have a specific comment about that initially, but the issue is, however, that when we are to run our stream of random numbers twice, we get different results. This should not be too surprising to anyone here that's ever set a seed before or is aware of how these pseudo-random number streams get instantiated. We can control this randomness by, in Python, putting a seed into our random.seed module, that method, or in R, we can simply do set.seed 1, 2, 3, 4, 5, 6, anything we want. And now we can control this stream of random numbers. Now, every time we run this snippet of 4 lines of code that's on our slide 7, I would guarantee with a large degree of confidence that you would get these same 5 floating point numbers that you see on the screen. There might be an exceptionally rare occurrence when you don't for some strange reasons, but almost sure as dang it, you're going to get these 5 numbers. And this is how we control randomness, right? So I can give this code to Ravi or Clint, and they can run the same snippet, and they should get these same 5 floating point numbers. So why do we care about this? I would argue that they're an invisible source of uncertainty in the scientific record. And I would like to ask you to think about this yourself. Have you ever ran a computer program that either you or someone else has written twice and got different results. Have you ever yourself set a seed to control this? Which seed did you select? Maybe you prefer set seed 42. This is a very common one. Some people like their birthday. Some people like 1, 2, 3. You can more or less, given current best practice, pick any seed that you want, and this shouldn't matter. Maybe you like using R. Maybe you like using Python. Why did you set this seed? Is this a lucky number? Does it matter? But you would have been motivated, I'd be pretty sure, to eliminate the variation in PRNGs by setting this seed, so that when you publish your paper, you can put your code up on GitHub, you can send it to the editorial office, and they can host alongside your article. And then someone else can come along, download your script, and be sure that you haven't done anything a bit too funny with the results, and everything is as is expected. And when they run your script again, they'll get the same number that you've got in your nice published article or conference proceeding or otherwise. This is not only the current best practice advice in terms of advice that we all, more or less, I'd be sure, currently give to our students, that we ask editors and authors to do when we're reviewing their articles. It's even rule number 4 out of the 10 rules for reproducibility in a very well cited and very famous PLOS Biology article of a few years ago. The general consensus is that you should set one seed because it allows other people to get the same result as you. This is very well intentioned, and this allows reproducibility. Yay! Let's see this in cartoon form. We have our researcher. His result is 42. He's finished his PhD, he's going to send his paper to the world-leading journal, and he's really excited. He goes to sleep and he dreams of being this famous researcher. He's going to win a prize, and that's in his dream. He gets this award, Nobel Prize or whatever it wants, because his result is really powerful. 42 is the most powerful number he could have got. It conforms with all of the theory. It's statistically significant. He's really, really jazzed. So he's having this wonderful dream. He gets up the next day and he runs his script again. And now his result is 97. And he can't understand what in the world has happened. So he's a bit perplexed. All of a sudden, his colleague comes along and his colleague says, hey, didn't you know? Didn't your supervisor tell you you need to set a seed for reproducibility? So he's a bit nervous by now, but he sets his seed 1, 2, 3, and his result is 62. 62 is a fine number. He might not win a Nobel Prize with this result, but he's generally pretty happy that, at least now his work is reproducible, and it's still a good number. It's still going to get published. He's having this dream. He thinks he's robust. He's, thinking he's invincible, as it were. So he's very confident now that he's still got a publishable result, and now it can be replicated by editors, reviewers, anyone else who comes along, finds his replication package, and runs his same script. Oops, my Acrobat has crashed. I might need to temporarily stop sharing my screen and reshare 1 second.
Yeah, I was thinking the same thing. This is like exactly the right moment to.
There we go. We should be back in business. So we have our researcher, and he's set his seed. His results are robust. His colleague comes along the next day, and his colleague says, so how did you choose the seed? Our researcher thinks it probably doesn't matter. Ah, my Adobe has crashed again. It might be the cartoons. With different PDF viewer. Our researcher is confronted again by his colleague, and she says, how did you set your seed? And our researcher says, well, does it matter? He now goes away and he tries a second seed. He tries 4, 5, 6. And now his result is minus 746. And he thinks, what in the world am I supposed to do? If I'd set 2 different seeds, my results change enormously. No one told him this when he was in graduate school. Our researcher, the protagonist in this story, didn't even know that setting a seed was the correct thing to do. However, because there's no guidance on how to set the seed, what we're going to argue in our paper and for the remainder of this presentation is that this seed does actually matter. Our researcher now is quite fretful because he doesn't know the scale of this problem and he has no idea what he should be doing next. He can't publish one of his results from one of these seeds because he knows in his heart of hearts that if he'd have chosen a different set of seeds, set or single value of seed, then his results could have been entirely different. This is a cartoon we're going to put onto Blue Sky or something in the near future. And this story, this kind of project came to light as I was having lunch with a colleague in 2019. This is how long we've been working on this project. And we were discussing the fact that we'd both reviewed a paper and we'd looked at their replication files, and the authors of that replication file had chosen a very strange and arbitrarily sounding seed. And I said to my colleague, well, don't you think it's strange that they've chosen 784.126.7982 as their seed? Maybe they've chosen this seed for some specific number because it gives them some good result. And my anonymous colleague then, who is not at Oxford anymore, so that de-anonymizes them a little bit, the anonymous colleague said, well, it shouldn't really matter. If the research is publishable in a high quality journal and they're using a relatively straightforward and well accepted method, then the seed is never going to statistically affect any of the estimands of interest that any researcher is really going to be interested in. And we thought about this quite a lot and we began replicating papers, and I'm hopefully going to convince you through a series of high profile replications, both modern and classical, that this is not the case, that this choice of seed actually has enormous effect on the variability of a large number of different types of estimands of interest. So the general problem statement for our setup is that by setting one seed in applied pipelines, we're ignoring the variation of our estimand. This is the variation in what the key number that we might be looking to get out of our algorithmic pipeline is. And this is a function of how we arbitrarily choose to set the seed. Setting one seed is computationally unintensive, but we think it's scientifically dangerous to do this. A solution might be to visualize the outcome space of a large number of seed trials. This could be 100, could be 1,000, it could be 10,000, could be 100,000. This is computationally intensive, but is scientifically responsible. The policy recommendations we're going to make at the end of the slide, at the end of the slides, after I've convinced you of how big a problem this is going to delineate and outline just how necessary and important this is to do. We can also think about replicating papers with large numbers of trials to see whether authors have done something known as seed hacking. Our original suspicion of the paper we first discussed in 2019 was that these authors had chosen a very favorable seed that made their work more publishable. And we can assess this through some kind of reproducibility lens by rerunning the algorithm with a large number of seeds and seeing if this one specific seed that the authors have chosen lives relatively near to the center of some distribution of interest. Maybe it's the distance to the mean value of the estimand, but it could more or less be any estimate. And we don't really want to give too many suggestions as to what that is because it's very flexible. So what do? We replicate about 20 very high profile papers. We show some simple simulated examples. We show how seed variability exists in data pre-processing. We show how it exists in modeling, in prediction, how seed variability can compound in pipelines when you have a stochastic imputation of data, stochastic building of models, stochastic folding of data to evaluate models, and so on and so forth. We show the implications of this on fairness and bias through a high profile recidivism example. And we also show how this affects LLMs too. We're going to conclude with some hopefully renewed best scientific practice. And all of our code is available on GitHub, and there's a QR code on the final slide. Anyone who's interested in reproducing our code. We think it would be quite hypocritical if we didn't make available all of our materials when we're replicating everyone else's, because our work is only really possible through the generosity of the academics who have come before us, who have made their code reproducible for reanalysis. And so much commendation and salutations to all of them for being such good open science scholars. If we think about some simple simulated examples in subfigure A on slide 13, we have an SIR model, a susceptible infected recovered type of model, very common in epidemiology. In the subfigure B, we have Buffon's needle problem. I don't know if anyone's aware of Buffon's needle problem. The idea is that you can approximate pi by dropping a needle on a wooden floor where there are planks on the floor, and the number of times that the needle crosses one of the vertical intersects of the pieces of wood, you can actually approximate pi. But depending on the seed that goes into the algorithmic pipeline that we do to replicate Buffon's needle problem in subfigure B, you can either approximate pi as 4.3 or 2.4, which are of course nowhere near pi whatsoever, all simply depending on which seed you instantiate your Mersenne twister with. Quite well studied in especially engineering undergraduate programs as an example of Monte Carlo stuff. And in subfigure C, we replicate a paper which shows the number of collisions in a 32-bit Mersenne twister, which is again, almost ironically, a function of the seed itself. So depending on what seed we set, the number of times out of 1,000,000 that we actually draw the same stream of random numbers is a function of the seed that starts that random number process itself. You can either get 150 out of 1,000,000 collisions, or you can get about 75, 80 out of 1,000,000 collisions, all as a function of what seed you set to start this stream off. This might seem inconsequential, but my most cited paper uses 1,000,000 or so, or 100,000, I forget, trials of a stochastic algorithm, and only something like 99.98% of them were unique. And I'm pretty sure that that's because we had collisions going on as a function of the seed that we used in that algorithm for that paper. Seeds occur everywhere. These are just 3 simple simulated examples, which are all directly and explicitly drawing from something like NP-random or any other language's equivalent. This is just to show you that without even beginning to think about data, building a specific model or otherwise, we have stochasticity in our pipelines that we are probably aware of here if we are directly calling np.random or otherwise, but in other scenarios, it's much more hidden. And let's talk about some of those next. Well, as we mentioned, those last examples using np-random or something else, we spoke about what exactly they were. Even in these simple trivial cases, seed variability is non-trivial. There are implications in more complex pipeline. Our next replications are going to involve examples from machine and deep learning, sociology, digital humanities, criminology, medicine, computer vision, econometrics, time series analysis, urban segregation, and large language models. As I mentioned at the top of the slides, we're going to talk about recent and classical papers. And for each of these next series of slides for the examples, I'm going to try and give you some intuition as to what's going on underneath the hood of these algorithms and exactly what's causing this seed variability, some intuition. First, and one of my most favorite examples is a re-replication of the Fragile Families Challenge published by Matt Salganik and his colleagues in PNAS in 2020. This is one of my all-time favorite papers. I think everything that Matt Salganik has continued to do along this trajectory has also been very worthwhile and highly readable. What the Fragile Families Challenge did is it solicited a large common task problem of about 155 teams of researchers around the world to try and predict life course outcomes of children in the Fragile Families Child Wellbeing Study between the ages of 9 and 15. And there was this common task problem where people tried to see if the results could be more or less accurate based on different approaches that the individual researchers might have made. The research design was wonderful because there was this nice holdout design between waves within the Fragile Families Challenge, within the Fragile Families Child Wellbeing Study. The teams were asked to calculate their outer sample predictions on a wave when children were age 9, but before the data had been collected when they're age 15, so there's no way to peek at the hidden data that was held out from the challenge. What was remarkable about the FFC is that this common sociological baseline with just 3 right-hand side variables in either an OLS regression or logistic regression was able to beat almost all of these 155 other teams of software engineers, computational social scientists. It was this somewhat naive sociological benchmark baseline that did really, 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 really well in this challenge. It won for, I think, 4 of the 6 target variables that the teams were trying to predict. And this was really curious to us. And we began to go through the application materials and the files, and they had specified a specific seed. And what happens in the Fragile Families Challenge reproduction materials, is that there's some kind of model data imputation. So they use a very commonly used library in R called Amelia 2. And Amelia 2 takes some form of stochasticity in exactly how it imputes missingness in the data. For those of you who are aware of the FFCWS, you'll be aware that there's a large degree of missingness. There are many, many missing observations within this data set. The challenge was already slightly kind of restricted in the number of observations that it had. It only has between, I think, 2,000 and 3,000 participants in its original source data set. And so to retain the dimensionality of this data set rather than dropping people, what the organizers of the challenge did in the data set is they imputed this using a stochastic algorithm. And on the slide, we can see this enormous array of both the beta hat from a more inferential type of baseline against the pseudo R squared, their out of sample model evaluation metric. And we can see that this varies enormously depending on the target, simply as a function of the seed that you set. If you run the imputation with 1,000 or 10,000 different seeds, the way that you interpret the performance of these models changes quite dramatically. The accuracy for out of sample R squared for GPA, for example, goes from below 0.06 to above 0.15. This is more than a doubling of the R squared or a decimation of the R squared, all simply as a function of exactly how we've imputed the data. Nothing to do with how we've built the model. And here there's one very specific train task split that isn't a function of randomness that we're going to talk about in a few slides' time. Here we can see that the interpretations of the results of the baseline model with this imputation strategy can vary quite substantially. However, we have no reason to be suspicious of the FFC at all, because with the dashed lines, we can see the exact beta hats and the R squareds that are obtained by the challenge organizers with this one specific seed that they've set. And this more or less always sits quite near to the middle of the distribution of the 10,000 seeds that we ran. It might have been that another more nefarious set of organizers had chosen a seed that maximizes or minimizes their R squared to have made a specific point, or before we actually begin to think about building models or cross-validating at all. So what's going on here? Well, Amelia is filling in missing data by drawing values from distributions. These distributions are based on observed data patterns, and this is a form of multiple stochastic imputation and results in entirely different models being built before we even get to run our first estimator on the data. This has implications for both inference and prediction, and that's why in our hex bin plots, we have both beta hats on the X and R squareds on the Y. This is not restricted to a prediction or an inferential problem. It affects all scientific pipelines when we have some form of stochastic imputation going on. Let's see another example. This is the topic modeling of large corpuses of different academic texts. We have the most 100,000 recent abstracts from Science, from the New England Journal of Medicine, from Nature, from the Journal of Population Studies, from PNAS, and a recent report that we wrote based on impact case studies submitted to the UK government for evaluation in the 2021 Research Excellence Framework exercise. And depending on how you set the seed, if we look at, for example, with any of these examples, actually the variation is enormous. If we look at, say, Science in our top left example, depending on how we set the seed, using BERT topic, one of the most commonly used topic modeling algorithms that I'm sure many people in the room today have experience of, you can either get something like 3 topics modeled on 100,000 abstracts, or you can get as many as over 600. With PNAS, this goes from about 3 topics to 1,200 topics. Other large examples in Nature, you can go from having 3 topics to 1,500 topics. This shows how unstable that one specific topic modeling algorithm is. But even if you were to use LDA topic or other forms of topic modeling algorithm, these would also be similarly unstable. One of the reasons why BERT topic as a topic modeling algorithm is so especially unstable is it because it uses a highly sensitive algorithm called UMAP that some people here might be familiar with. And we have some work specifically that looks at the stability of UMAP as a function of seed in the supplementary information of the paper that we're hopefully going to be pre-printing soon. So when we come to applying topic modeling algorithms that rely on seed, the number of topics, and of course, which topics they represent, because these are amalgamations of subtopics and groups of topics together into high-level aggregates, can vary enormously. And we would argue this is quite surprising. We haven't, cherry-picked or hand-picked. These are literally just the first kind of few journals we thought of replicating, and then we didn't need to replicate anymore because the variation was already enormous. But very happy to replicate other journals. You could send us ISSNs. Please, Ravi.
I just want to make sure I understand how you're generating plots like these. So, uh, is it correct that you're choosing a seed and then reproducing the results, and then choosing a different seed,
Exactly so.
reproducing the
Yeah,
results? And
I
so,
should
how
have
are you
been clearer.
choosing the different seeds?
We are going to come to this at
Okay.
the end. For now, I think all it's important to know is that we can just think about this as living within a nested within a for loop, right? For the sake of convenience, let's for now think of these as being four seed in range 0 to 1000. Then do algorithm, save result, plot result, something
Okay.
like that. But we are
Thanks.
going to come to exactly how we argue that you should be choosing the seeds, yeah. But that's all of the following plots are going to be of a similar design in that we're rerunning essentially a core baseline algorithm more than once with a different seed. And the whole story of the paper is not more convoluted than that. But I believe that the results are sufficiently surprising that you'll hopefully find them interesting, even if the design doesn't change enormously. So what's going on here? We have BERT topic, a fabulous algorithm that we've used many times. It commonly involves UMAP. UMAP causes different low dimensional embeddings based on how we set the seed. If we're using HDB scan for clustering, there's no seed variability. And here in particular, as with many of the examples, the variability is enormous, right? This is of enormous consequence if we're publishing a topic modeling exercise and we're not aware of the fact that by setting the seed to something different, we could have got an entirely different distribution of estimands of interest and topics that come out of this algorithm. This isn't a very small perturbation where we go from 56 to 55 or 56 to 57 topics. It's orders of magnitudes of hundreds of different topics more, which is why we include this. For the more kind of conventional statisticians in the audience, we have a maximum likelihood based example. This is using the MV Proba estimator in Stata. We didn't want to just pick on R or Python users. We wanted to pick on other languages to show just how ubiquitous this problem is. This is an estimation that shows the effects to do with educational attainment and schooling and things like that. It's a replication of a paper that introduces this multivariate Proba estimator package in Stata that's got several hundreds of citations is an immensely useful package in general. What's going on here in this classical statistical or econometric sense is that we have to evaluate M integrals jointly, which gets rewritten into several multivariate normal distributions. We then sample from this to get the underlying likelihood, and it's this sampling of the CDF which gets us some kind of value in a uniform range of between 0 and 1 that is seed dependent. So even if we have, a very traditional economic or statistical inference problem where we want to get this estimand of interest and make some statement about whether this estimand is statistically significant, all of the variability caused by seed is being hidden. For sure, we have our conventional sampling errors, right? We have our t values and our p values, and everyone is very well aware of how we can calculate confidence intervals from them. But this compounds with seed variability. So we could have multiple forms of variability affecting the certainty of our estimand. And one of the things that I'd like to argue in general is that when we're using stochastic algorithms that also have sampling variances, then we could be severely underestimating what our confidence intervals are, where seeds are being ignored under more than one type of variability at play. When the CDF is steep on a small interval, seeds matter a lot. This is just one example of one application of applying the MV Proba estimator. As I mentioned, this is in Stata, and all of this code is available online on our GitHub repository. Let's see our next example. This is to do with the Schelling model that some of you might be aware of, the Schelling segregation model, which is how people move around a grid of squares based on who lives next to them. This is more or less simulated, but we show that the performance and kind of patterning of these algorithms changes quite substantially as a function of the seed. Here we have 4 different parameterizations of the model of different grid sizes and different happiness thresholds and things like that. But simply depending on how you set the seed, which randomizes A, both how the initial allocation on the grid is determined and B, how the people move around, we get some quite substantially different patterning at each step across our convergence range. It also takes a different amount of time for each of our kind of systems to converge conditional on how we set the seed. We think this is quite a nice classical example that this very famous social science model is again very contingent on how we initialize our random number generator. Yeah, as we mentioned, it depends on the initialization of agents on the grid, the shuffling of unhappy agents and cells. Agents might be more or less segregated from the beginning, for example. And even if the model reaches similar segregation, configuration of the agents within some kind of homeostatic stable state will differ, as will have their trajectory towards that steady state. Parameterization in all of these things matters quite a bit, which is why where we can, we've tried to present results across different parameterizations while focusing purely on varying the seed in each of these models and parameter spaces. We also have a set of examples for time series econometricians, if there are any here. You might be familiar with the random walk, which is used as a benchmark for most time series forecasting types of exercises. When I was doing my PhD in time series econometrics, computational time series econometrics, the norm was very much to use the random walk as a baseline benchmark model for which we could compare our more sophisticated model. There's an extraordinarily influential paper in the 1980s about how random walks are the best way to forecast foreign exchange markets. And so what we do is we replicate that paper and several other types of assets where we replicate the price of Bitcoins, the NASDAQ composite, or the NVIDIA share price. Depending on how we set the seed for these models, a random walk could either predict that the value of the NVIDIA share price is going to be $1,400 a share, or as low as what looks like to be $30. Same with Bitcoin. Bitcoin could either be as low as $10,000 per coin, or as high as $300,000 per coin. You can tell that actually this example a short while ago, because Bitcoin is now much higher in value than it was when I ran the in sample, the blue line here. So simply depending on how we set the random seed, this canonical key benchmark in time series evaluation can give you either a very reasonable and competitive denominator for the root mean squared error of some other estimator that you're benchmarking against, or it can give you something absolutely wild that's going to be nothing like the reality and is only a function of this one random number stream, giving you a series of highly improbable steps moving forward. What's going on here? Well, seeds modify the PRNG draws, which affect the time path of Y. The moments of previous changes are controlled by the magnitude. This is stochastically based on draws and a mean value of the previous parts of the walk. This impacts the trajectory quite steeply. The seed affects the long-term trends at each step. It can be formally written as in equation 1. It was previously thought, as I mentioned, that nothing outperforms random walks for foreign exchange markets. This is a very famous Fama and French paper, I think. I might be getting the names wrong. I have to go and check a paper that replicates this. And this is used as a benchmark for everything from foreign exchange markets to dynamic stochastic general equilibrium models, DSG models, and beyond. So we've previously spoken about examples of A, inference, imputation with the fragile families challenge. If we go back a slide or two, we have an example of imputation where we're imputing using a stochastic algorithm enormous effects on parameter and evaluation space. We've then gone into some other examples which look at how seeds affect how we build our models, our UMAPs, our estimators, our Schelling models, our random walk models. It also has enormous consequence for predictive models specifically. This is because many predictive models have both some kind of stochasticity in how those models are built. If we're thinking about random forests, this is how features are partitioned. If we're thinking about neural networks, it's about weight initialization. And importantly, it also has implications for how we fold our data in more conventional train and testing splits, our K-folds. Our K-folds are a function of random numbers, right? How do we know exactly where we need to be folding our data across our entire data set? We can see this in the top left hand example, subfigure A. What we do here is we replicate a highly influential COVID-19 paper, which showed that simply with symptom tracking applications, before tests were widely available, that with symptom tracking applications, you could very, very, very accurately predict whether someone was going to positively test for COVID. And this was a very highly regarded paper, which I very much enjoyed reading. But if you replicate this paper simply as a function of how you fold your data, your ROC-AUC decreases to 0.68, or it increases to as high as 0.8. This has enormous implications for clinical practice, for whether tests would have otherwise then been developed or not. I'm sure they would have been, but this can guide high profile policy responses to clinical events. If we're folding our relatively deterministic model in a specific way, this has enormous implications for how accurate our model is going to be. We can see examples in subfigures B, C, and D, and E, F, and G of things like predicting survival on the Titanic dataset or predicting house prices in California. Here we have random forests and folding. We can decompose and back out the variance of our outcome of interest as a function of whether our seed is affecting the partitioning of our data that goes into our model estimating, or whether the variability within the entire pipeline is a function of how we're folding. So in the yellow histograms, we have this decomposition into effects that come from modeling or from folding. And the blue in subfigures B and E are our total distribution of things like the R squared, or in subfigures E, F, and G, the intermodal vigorish, a wonderful new evaluation metric, which I highly recommend to everyone to use. And in subfigure H, we can see that with the MNIST data set, which is about image recognition, there's 10,000 different handwritten characters that FedEx need to try and scan and then send your parcel to the right place. Simply as a function as to how you instantiate the weights in your convolutional neural network, you can either predict all 10,000 digits perfectly correctly, or you can get as many as 1,100 or so wrong, simply as a function of how you initialize the weights based on how you set the seed for this CNN, which is quite alarming and again has enormous implications for downstream accuracy as to whether technologies like this end up getting utilized in practice. What's going on here? Well, we're mostly talking about stochastic folding, but we're also talking about weight initialization. Stochastic folding happens with almost every form of cross-validation. The only exception is if we leave one out. If we fold our data if we fold our data in such a way that we estimate, train our model on everything but one observation, test on that, and then repeat that for every other observation, then we have no seed variability because we've deterministically sliced it in a way that's not subject to randomness. I think that we're going to finish our paper by working on some asymptotic results in regard to how many splits, how many folds you have. I think it's very much that the fewer the splits you have, the more randomness, the more seed variability there is. So for example, if we just have one deterministic train test split at 0.5, then your seed is really going to kill you. If you have 5 splits at 0.2, 0.4, 0.6, 0.8, then 1. If you have 5 folds, I should say 4 splits, then your seed variability is going to matter less. And asymptotically, as you go to leave one out, then your seed variability, the seed that you choose is going to be less influential. We can decompose types of variability within model building and folding in certain specific ways. And the final example in our subfigure H shows this with no CV folding, there's only model variability. I'm going to speed up a little bit because we're running a bit short on time. We've got this wonderful Figma diagram through a co-author, and they show in this diagram how seeds can compound across parts of the pipeline. The idea is that this pipe at the bottom is kind of getting larger as we go through our data processing, our model training, and our model evaluation, our folding, because all of these three things can explode the distribution in the estimand space that we might be interested in. So we approach this by building a simulation that uses causal forests, a wonderful paper by Susan Athey et al., published in around 2017, 18, 18, 19, I should really know, an exceptional paper. And here what we do is we stimulate some data based on one fixed seed with missing at random. We then impute this. We then build our causal forests, which have got both predictive and inferential connotations to them. And then within this, we also have folding. So we're able to show, although we haven't parameterized this model extremely well, that in the blue of subfigure A, the variation in our estimand of interest, the average treatment effect, or this tau parameter, as they call it in their paper, is actually wider if we have multiple sources of seed variability in a model than if we just fix a seed at any one specific part of this pipeline. This is the idea that as we go along the pipeline, if we have more seed variability, the distribution at the end of our results can actually explode. We want to kind of quantify this further in the paper to see whether it's multiple imputation, model building, or folding that drives the primary source of variability in the outcome space as a function of seeds. But it's our opinion at the minute, at least, that it's very much the folding that is causing variation as opposed to model building. If we're folding our data in one specific way, this is incorporating and bringing in more variability to our pipeline than the other sources of seed variability that we've been able to commonly identify. So importantly, this example shows how seed variability compounds. We simulate one data set, we use mice-style stochastic draws, we use this nice causal forest package by Susan Athey et al., and we compare various seed varying schemes where we fix one seed randomly for all of the types of seed variability, where we just vary for model imputation, where we just vary for model building, where we just vary for evaluation, and then we vary them all at the same time. That's our kind of rough design there with lots of different seeds. I think there we only use 1,000 seeds rather than 10,000. In many of the other examples, we've used 10,000 where computation allows. We're going to end on our final slide talking about that. We have various different simulation parameters. My co-authors and I are working on how we can perhaps better parameterize this model to better show the effect of compounded seed variability. It's a work in progress. One example that I'd very much like to spend a minute or two talking about are these applications to bias and fairness. So what we do on slide 32 is we replicate a very high profile ProPublica data set that tries to predict whether individuals are going to commit a crime if they are paroled, a recidivism data set. We use logistic in columns A and D, random forest in B and E, and a shallow neural network and multi-layer perceptron in C and F. And here we show that depending on how you set the seed, your probability of reoffending changes 51.9% of the time. And I think that when you subset this on Black people, then this goes up to 58%. I don't know exactly what those numbers are because I can't quite remember, but this basically shows the percent of times that a number can flip above and below 0.5. We have yet to kind of figure out exactly how data sets like the ProPublica data set are used in practice. It's very unlikely that criminal justice systems are either naively setting this 0.5 threshold above no parole, below yes parole. It's surely more complex than that. And it's also extremely unlikely that they're going to be folding using anything less than leave one out cross-validation. I think that we have conversations with criminologists lined up who know much more about the use of this type of algorithm and this type of data set in practical settings. But the rate at which the flip from above to below a 0.5 probability is enormous. So hopefully this is of interest. There are other applications here in terms of mortgage access and inequality, and also healthcare settings where there we think that decisions in practical real life situations are going to be changed simply as a function of how random numbers are generated. The final, maybe quickly say about Compass. This emphasizes the implications for distributional fairness. The framework that ProPublica replicated is known as Compass. Seed variability because of both model instantiation and folding. In our leftmost column, A and D, we only have a logistic regression, so there's no model variability as a function of seed there. It's much narrower because we just have folding, not modeling as well. We use this famous ProPublica data set. We repeat twofold outer sample cross-validation. We specifically only fold twice. This engineers some degree of artificially high seed variability, and we summarize in various ways. There are various different extensions using other more commonly used metrics of fairness like statistical parity. And the final example, which I would like to talk about, is something we've been working on over the weekend. And this is when we query large language models. Either we prompt the large language model to say that it is old, upper class, lower class, other social characteristics that are associated with being Republican or Democrat. And then we ask it to choose one of 11 words which describes either that person's own party or the other party which it's not identifying as. So we have described by Republicans, describing Republicans, described by Democrats, describing Democrats. And this shows the variability across the seeds, across a range of different temperatures. You can get almost any response for some of these things based purely on how you set the seed. This might seem like a relatively fanciful example, but this is one of the most common uses of political attitudes types of surveys within the social sciences at the minute. Some of the most highly cited LLM papers in the social sciences are in political sciences, where they're priming LLMs to respond to surveys. There are even a substantial number of companies that have been set up to do political consulting that are using these synthetic large language model responses. And we show that this is especially unstable in general, not just as a function of temperature. Actually, it turns out that the temperature of these models, this is a GPT-4 for every 2025 frozen state model that we use for reproducibility purposes. The temperature actually doesn't matter that much, and the seed really does matter a lot. This, I think, is not unknown, but we quantify this quite nicely. And we also show that in 2 of these 4 examples, the quadrants of this figure, even when you set temperature at 0, the seed can affect a stochastic result, which is potentially problematic, because at least if you set the same seed in other parts of this research, you can get the same number back. Here, if you set the seed and the temperature, it can still give you something stochastic. And there are some technical reasons as to why this is that we can maybe talk in a Q&A or via email after this. This is just to simply describe what we've done with the large language model example. Let's go to some concluding thoughts. Matt Salganic, one of my favorite computational social scientists, I had a chance to discuss this with him because he also wrote the Fragile Families Challenge. I said, hey, Matt, we're replicating your wonderful paper. How do you think about this idea that seeds can have this effect? And he said, well, this is really great. This is fantastic work, but it sounds very computationally expensive. I have tried, and I think succeeded actually, to run all of the examples that you've seen here today, either on a relatively underpowered desktop or laptop. A couple of the scripts might have taken 8 or 9 hours, but I was very deliberately motivated to try to avoid using high performance computers for any of this research, not because I don't like high performance computers or have concerns about carbon cost or otherwise. If anything, I'm causing more carbon cost by running it inefficiently on my laptop. This is to show that while this is a relatively computationally expensive thing, it's not computationally prohibitive. You should be able to run these on whichever device you're looking at this talk on now, unless you're on a phone. Even then, phones are so powerful these days that I'm sure you could replicate things 10,000 times using a mobile phone, an M5 chip, for example, or an iPad. What are our suggestions? Well, researchers should visualize their seed variability where affordable. There are times when you can eliminate this entirely. That's when you move from a 5-fold to a leave one outfold cross-validation type of schema. We should teach students how to parallelize their code effectively so that they can distribute their workloads across either CPU or GPU cores to enable the running of a script 10,000 times in a relatively tractable way if they're on a 32-core machine or something at the university. When you're reviewing papers, either as a reviewer or an editor, you should question, is there stochasticity in this algorithm? Should we be requiring the authors to estimate their experiments with a large number of seed trials? Even well-established results are susceptible to seed variability, as I've tried to convince you of today. We think that the editors should mandate multiple seed trials being ran across all of the papers that they're accepting. There is a very small pocket of computer science conferences where this is expected, but not always adhered to by any means. And there we're talking about some very computationally expensive things. And so researchers might only use 10 seeds. That's fine. We argue that this should become the ubiquitous practice. In terms of Ravi's question, what seeds are we talking about? These could be as simple as just running your seed in a loop across a range of 0 to 100,000 to 10,000 to 1,000. This is absolutely okay. This is far, far, far better a universe than where we've just arbitrarily picked our birthday or 42 or 123 or anything like that. So this is absolutely fine. We have a couple of examples in our replication package where we have actually done this just to show that this is a fine approach. A slightly better approach is to use this predefined list of secret seeds that we provide on our GitHub account. That's because you could have arbitrarily specified for seed in range 0 to 1,000, tried all of your 1,000 seeds, got a set of results you didn't like, and then you could have done for seed in range 1,000 to 2,000, 2,000 to 3,000. And you could have done this as many times until you had found a set of results that you liked. However, we generate a set of 1 million 32-bit and 1 million 64-bit seeds that have got a range of nice favorable properties. And we would like to implore everyone interested in this type of work to simply download our seed list. There's no need for attribution. We make it available under a GNU GPL 3.0. You don't have to cite, you don't have to acknowledge us in any way. But by using the first N seeds of that seed list, because it's predefined, it's almost pre-registered, you then could not ever latterly be accused of seed hacking. So this list is publicly available, and we think that this is a good thing to make available because it prohibits people from choosing a range that they like. The only danger with this is that people could try to run their pipeline with 0 to 100 of the first elements of our seed list, decide they don't like their results, and then run for 0 to 200 and basically have a stopping rule that as soon as their p-value becomes less than 0.05 or their r squared goes greater than whatever threshold, then they stop. That's the only danger of this approach. We can't really think of anything better. In NumPy, there are bit generators, which are extremely useful, but a little bit harder to use. And we think that in the future is going to be quantum random number generators. So there's a wonderful bit of research that is going on at the minute to make accessible and available high quality quantum random numbers, which are provably truly random for academic research. That's very exciting. The main takeaway from the talk is that we want to move past this idea of setting one seed to get one outcome that can then be reproduced. You want to be setting multiple seeds that can also be reproduced, but give you this distributional aspect of all of the results that you could have got had you have chosen any one of these other seeds. We think that PRNGs shouldn't exist for the purpose of random numbers. The future is quantum. Your results should be reliable to a stream of truly random numbers, regardless of what stream that is. At any one point in time, your results should be stable, just in the same way that it shouldn't really matter if you choose 1,000 different streams of PRNGs. Any stream of quantum random numbers should also give you the same takeaway regarding your estimand from an intuition type of point of view. There might be lots of other types of seed variability. As I've been talking, I'm sure that you've thought of some times when seed variability could have crept into specific things that you've been reading or you've been working on. Seed variability can be corrected. So papers like ours try and bring attention to this, and it shows the range of estimands of outputs that you could have got had you specified any other different set of seeds. We're thinking about making an index of historical papers that get replicated with a large range of trials of seeds in a way that, doesn't necessarily have to correct the scientific index, but it makes it more transparent as to what this range of numbers could have been. We make available this list of seeds, and when variation can't be eliminated, we argue it should be visualized. We have two wonderful co-authors, one of my current PhDs and my first PhD students. Thank you to you also for your attendance. And if you're interested in learning more about this work, we have a Dockerized container on GitHub that you can go and play around with, and we should be updating that in the coming days when we also make a preprint available. So apologies for the Adobe issues, but thanks for your attendance.
Thank you so much. I'm going to clap on behalf of everybody.